All right, well, thanks very much for the invitation. It's really nice to be back. Like Robert, I have sort of a memory of being in this room very early in my time at Princeton, except instead of Bob Gunning standing up at the front in a bow tie, it was John Conway in a very old T-shirt. Okay, so yeah, I wanted to talk about, well, L spaces in freshman calculus. It's maybe not quite the title that I sent in originally, but I think it's more accurate. So maybe let me first just start by recalling what an L space is. So let's recall that HF hat of Y splits over spin C structures. Oh, and before I go any further, say that everything I'm going to talk about is joint work with Jonathan Hanselman and Liam Watson. And a lot of it is based on earlier work that I did with Sarah Rasmussen as well. Okay. So coming back to HF hat of Y, we know that this splits as a direct sum over, let's say, S in spin C of Y, HF hat of YS. And it's a theorem of Oshvath and Szabo that if B1 of Y is 0, then the dimension of HF hat of YS is always at least 1. Okay, and I wrote dimension here, and that's because everywhere throughout the talk I'll work with Z mod 2 coefficients. It's always over the size 2. Okay, so an L space is a manifold where the Floer homology is as small as it can possibly be. So this dimension is 1 in every spin C structure. Y is an L space if the dimension of HF hat of YS equals 1 for all S. Okay. So now maybe the next thing I should talk about is Dehn filling. Here I just want to set up some conventions. So throughout the talk, Y is going to be a closed manifold, and M is going to be a manifold with torus boundaries. So M3 is compact. Boundary of M is T2. Okay, then we can talk about the slopes on boundary N. Set of Dehn filling slopes. This is alpha and H lower 1 of Y, such that alpha is primitive, not a multiple of some other class. So it can be represented by a closed curve and then modulo plus or minus 1. And if I give you a slope in boundary M, then I can Dehn fill. So M of alpha, that's the Dehn filling, is M union phi with a solid torus, S1 times D2, where phi of the class of boundary D2 is this slope alpha. Okay. And so now, the questions that I really want to talk about in the talk, the first question is this. So given M, so when is the Dehn filling M of alpha in L space? Okay, so like Matt said in his talk, this is a kind of a splice. It's a very special splice. But we could also ask the same question for a more general splice. Question 2. When is, let's say, take two manifolds with torus boundary and glue them together, M2, an L space. Okay. And so you might ask, why might you be interested in these questions? So there's a conjecture that maybe now goes by the name of the L-space conjecture. I don't want to spend a lot of time on this, but this was the sort of underlying motivation for our interest in these questions. And what the conjecture says that if I is prime, then we should have y not being an L space is equivalent to pi 1 of y, let's say non-left orderable. I don't want to spend any time on finding these terms, which is to y admits a foliation. Okay, this is a very interesting conjecture. I won't say anything more about it, but sort of, let's see, y is, yes. Okay, L is, thank you. Okay. Yeah, so it's an interesting conjecture because it relates three very different things. So, of these different things leads you to these sorts of questions on the Floer homology side. So what's the tool we want to use to study these questions? So the tool is an invariant for three manifolds with torus boundaries that Liam and Jonathan and I introduced. Maybe the theorem is that there's an invariant, and I should probably credit this theorem, so Hanselman, self, and Liam. Let's just call it HF hat. For them, where does this live? Well, one way that you could say it is that it lives in the Fukaya category. Let me say TM. Where what is TM? TM is just my name for a punctured torus that's associated with manifolds. So you could think about it as being the boundary of M minus a point. Or if that seems a little bit non-canonical to you, you could also think about it as being h lower 1 of M with coefficients in R modulo h1 of M with coefficients in Z minus the origin. The origin's a nice canonical point. And both of these are good ways to think about this space. Now, I don't want to say too much about what the Fukaya category is. The good news is that in this case, you can think about this very concretely. So HF hat of M is a collection of closed oriented immersed curves in TM. Well, maybe they're equipped with local systems. So that means that I have to decorate each curve with some vector automorphism of that vector space. That's what a local system is. In practice, all the curves that I'm actually going to think about in this talk, the vector space is one-dimensional, and a one vector space over the field with two elements only has one automorphism. So there's really no choice to be made. Okay. All right, so now I should, for the next few minutes, I'm going to tell you a few things about this invariant, and then we'll see how to use them to study these questions over here. So first, let me talk about spin C decompositions. Just as in the closed case, we can split this thing up over spin C structures. And to do that, what we do is we consider a covering space. call it, let's say, P mapping from Tm bar to Tm. So this is a cover of Tm. What cover is it? Well, I need to tell you pi 1 of this space is a subgroup of pi 1 of Tm. Right? That tells you what cover it is. And what subgroup is it? Well, pi 1 Tm bar is the kernel of the map. Well, I start with pi 1 of Tm, which I could think of as boundary of m minus z. That naturally maps into h1 of boundary m. And now I can just include that into h1 of m. Okay, so this is the kernel map. Okay. And so what does this covering space always look like? Well, it's always a cylinder. For example, m is z. It's like a sort of infinite. So it's a cylinder with a bunch of punctures on it going down like this. And in general, it might not just one punctures here. For a general 3 manifold, I might have, for example, different sets of punctures the same height. Might happen. Okay. But it's always a cylinder. And if I forget about the punctures, pi 1 of this cylinder is just generated by this single curve here. What is this? This is, let's call this lambda. Lambda is the so-called homological longitude. So lambda generates the kernel of the map from h1 of boundary m into h1 of m. Okay. All right, so I have this covering space. And then the statement is that there's, if S is in spin C of m, so as a set, this is basically the same as h upper 2 of m isomorphic to h lower 1 of m relative to boundary. Okay, so if I give you a spin C structure, then there's an invariant hf hat of ms, which is in the Fukaya category of Tm bar. So it's some still a collection of closed curves. And how's it related to this invariant that we wrote down over here? Well, if I take the union over S in spin C of m of P, I can project down to Tm of hf hat ms. This is the thing that I called hf hat of m. Almost always it's easier to think about these curves inside of this cover. Okay. So maybe at this point it would be good to have a few examples. So the first example that we should do is probably S1 times D2. That has H1 of m equals Z, so this cover is a cylinder like that with one row of holes down the front. And what's HF hat of m? It's just a single circle that goes around like this. Okay. How about I have m is the complement of the trefoil knot. Okay, so then this cover, well, it's a little more complicated maybe. It's a curve It looks like this, and then winds around the back of the cylinder. So maybe just one more knot just for example. So if I take S3 minus the figure 8, this knot is somehow eponymous. So the interesting part of its invariant is a figure 8. It also has a circle that goes around the back, just like the S1 times D2 had. And notice, so this is an example where the curve has more than one component, and also it's not embedded. Okay, so these things definitely do happen, and they happen in very simple manifolds. Okay, so let me give one example that's not a homology S1 times D2. So if I have M, let me write it this way. So this is D2 1/2, 1/2. So this is a Seifert fibered space over the disk. It has two exceptional fibers, each of weight 1/2. So then there are two spin C structures, S0 and S1, let's say. And example, more than one row of dots at each height. Here I have 2 rows of dots at each height, 2 dots at each height. And so in one spin C structure, the invariant looks very boring, sort of like the invariant for the M knot, S0. And then in S1, it's a little bit more interesting. It kind of weaves around these 2 points. Okay. This invariant good for? Well, there's a pairing theorem. It says that if I glue 2 manifolds with torus boundary, I can use the invariance of the pieces to compute the invariant of the whole thing. It says that this way, HF hat of M1 union along phi with, let me write hom of HF hat of M1, phi of HF hat of M2. So you've seen one of us talk about this before, which many of you surely have. It used to be that we had a copy of the elliptic involution in here, but I think we can now prove that this thing is invariant under the elliptic involution, so I don't have to write it down. Okay, well, what is this hom? Well, this is hom in the Fukaya category, which sounds scary, but is actually very simple to compute because these are just curves. So if gamma 1 and gamma 2, no disks or annuli, in other words, they're in minimal position and they don't have any parallel components, then the dimension of hom of gamma 1, gamma 2 is just the number of intersection points between gamma 1 and gamma 2. And that's something that's very easy to compute from a picture. And if you want, for example, the Z mod 2 grading on HF hat, that's given by the sign of intersection between these two oriented curves. Again, that's very easy to compute. So maybe just as an example, let's think about surgeries on the trefoil. I drew the invariant of the trefoil up there. It's a little bit easier to see things if we unroll this cylinder to produce kind of a diagram in the plane. When I do that, I get a curve looks like this. And the picture, well, it came from unrolling that cylinder, so it's invariant under translation by lambda. Right. And so then, for example, on the other hand, I know that the invariant of S1 times D2 is just a, if I unroll that into the plane, I just get a straight line. So to compute HF hat of a Dehn filling at slope alpha, alpha is, let's say, hom HF hat of M with, let me just call it L alpha, where L alpha is a line slope alpha. So for example, if I wanted to do +1 surgery on the trefoil, I would draw this line with slope 1. I would see that there's exactly one intersection point. HF hat of +1 surgery on the trefoil is one-dimensional. That's because +1 surgery on the trefoil is the Poincare sphere. And if you know your HF hat, well, it has one-dimensional hat. On the other hand, if I wanted to do -1 surgery, that would correspond to looking at the intersection with this green curve. Here I see 3 different intersection points, and there's no way to isotope them away. I can't slide this curve over this puncture here. So I'm really stuck with 3 intersection points. So dimension of HF hat of -1 surgery on the trefoil is 3. And actually, just by counting the signs of intersection here, you'd see that you have, say, 2 generators in one mod 2 grading and 1 generator in the other. I'm getting overly enthusiastic about moving these boards around. Let's leave that here. Okay. All right, so, now there's sort of one more thing that I want to tell you about this invariant, and that is, well, sort of fancy word I could use to describe it is its decategorification. That's a very long word for a simple question, okay, which in this case is, I give you a closed-oriented curve or collection of curves in the space Tm or Tm bar, and I could ask, what's its homology class? Okay, that's what its decategorification. You know, the decategorification of the Fukaya category just gives you the homology class of the Lagrangian. So, well, let's say just in Tm, so downstairs, the homology class of HF hat MS, so I'll just fix one spin C star. I guess I should have written a P here because this lives up in the cover and I'm projecting downstairs. Well, this is always very simple. It's either a homological longitude if B1 of M is 1, or it's 0 if B1 of M is bigger than 1. Since I have torus boundary, B1 always has to be at least 1. And you can see all of these examples that we drew up here, they have B1 equal to 1. And if you just forget about the puncture points here, you'll see that these curves are all isotopic to just the curve that wraps once around the cylinder, which we said was lambda. Okay, so that's one form of the homology class, but I could also think about the homology class of this curve upstairs in Tm bar. So so in Tm bar, the homology class of HF hat of MS is determined by and determines the Toriev torsion. Okay, so Toriev torsion is apt to be a little unfamiliar to some of you, so maybe let me say a few words about it. So this is an invariant that assigns, so if let's say S bar is in spin C of M boundary M, if you don't know what this is, you should just think that this is the same as H upper 2 of M boundary M, the same as H lower 1 of M. Then the Toriev torsion tau M of S is some integer, S bar. Okay, so for every relative spin C structure, I get some number. That's, that's maybe not such a good way to think about it. Instead, I should think I combine all of these things into a generating function. I say that tau of M is the sum, let's say, over S in S bar in spin C of M relative to boundary of tau M S bar, and then I multiply by, let's say, S bar minus S naught. I fix a reference spin C structure. Then this difference will just be really honestly an element of H lower 1 of M. Okay, so this is an element of the group ring Z of H1 of M. Okay. And what is this element? So now we come back to things that may be more familiar to most of you. So, e.g., if H1 of M is Z, so then the group ring Z of H1 of M is just the same as the ring of Laurent polynomials. And, I told a little bit of a lie here. It's not true that there are finitely many non-zero terms in this sum. Actually, there are typically infinitely many when B1 equals 1. So this really lives in sort of a Laurent completion of this. Okay, so this is the Laurent series ring. I have finite sums and negative powers, but I could have sort of infinitely many terms with positive powers. Okay, so then this function that I called tau of M is none other than the Alexander polynomial of my manifold divided by 1 minus t, maybe up to global shift by powers of t. Okay, so that's that's something nice and familiar. All right, so what does the Toriev torsion have to do with this HF hat of M? Well, I can identify, let's say this. So given some S in spin C of M, I have an inclusion map, I mapping from spin C of M boundary to spin C of M. This is modeled on the map that takes H1 of M to H1 of M relative to boundary. Okay. And so the set I inverse of S can be identified with, let's say, the set of puncture points in Tm. Yes, that is Tm bar. Thanks. Okay, so again, say H1 of M is Z. We just have this picture here. So maybe this corresponds to, then we just have H1 of M relative to boundary is 0. Okay, and so I'm saying that these points here are identified with a set of spin C structures. So maybe this is S0, S1, S2, S minus 1. Okay, and this identification is equivariant with respect to the obvious action of H1 of M. Okay. And so now, what is this tau M of S? This is, let's say, gamma S dot HF hat of M I of S. Oops, this is S bar, relative spin C structure. Where gamma hat of S bar, so if you give me an S bar, that's one of these points. Gamma hat is a path from there down to minus infinity. So all the way down to minus infinity. Path from, say, ZS bar to minus infinity. Okay. So for example, over here, right, if I draw a path from here down to minus infinity, there's no intersection with this pink curve. All right, so this number is 0. Similarly here, this number is 0. On the other hand, if I draw this path, I get intersection number 1. Okay, so what this says is that tau of M is 1 plus t squared plus so forth and so on. This is giving the 1, this is the t, which is 1 over 1 minus t. And 1 is indeed the Alexander polynomial of S1 times D2, so that's okay. Similarly over here, this point here will give me a 0. So is this one. I can go without touching this pink curve, but this is a 1, this is a 1, and all the higher ones will be 1 as well. So in this case, tau is going to be 1 plus t squared plus t cubed plus so forth and so on. And you can check that that's 1 minus t plus t squared over 1 minus t. Okay. All right. So I think that that's really all that I want to know about this invariant. So now let's go back and talk about L spaces. And maybe let's start with the definition. So if M is some manifold with torus boundary, then I can look at, let's call it L filling slopes. This is alpha in slopes on boundary M, such that the filling M of alpha is an L space. This is the thing we want question 1. Okay, and we'll say M is Floer simple if there's more than one element in this set. It contains more than one element. Okay. So now, so I'd like to state a theorem, but before I state the theorem, I need to maybe introduce one piece of notation. So let's consider alphas and slopes bounding M. Let's consider the map. Let's call it pi alpha, mapping from H1 of M with R coefficients to R. That just sends X to alpha dot X. Okay, so the fibers of this map are exactly the lines of slope alpha. So, and if alpha is not equal to the homological longitude, this descends to give me a map, which I'll still call pi alpha, that maps from Tm bar to S1. Okay. I just take the cylinder and I project along lines of slope alpha, and the quotient is a circle. Right. Okay, so then the theorem is that M is Floer simple if and only if the following condition holds. So there exists some alpha such that the map pi alpha, you can think about applying that HF hat of MS for some spin C structure. That map carries over to S1 by a homeomorphism. Okay, so it's a nice bijection between here and S1. Okay, and I have to put the small print about local systems in. All local systems have dimension 1. Okay. All right, so I've erased my trefoil, unfortunately, but so we still have, for example, S1 times D2. Right? We can see that this is Floer simple for just about any filling slope I choose, right? This, whatever I project, this is going to give me a homeomorphism. And so is this guy here. But on the other hand, this figure 8 knot is terrible. I'll never have this condition satisfied. Okay, so maybe let's continue with statement of this theorem. So if that's the case, then this alpha is actually in the interior of the L space interval of M. And we can say precisely what this L of M is. So say it this way, the interior of L of M is all the slopes on boundary M minus, say, the set of alpha slopes on boundary M, such that alpha is tangent to any representative of HF hat of M. Okay, this thing here is sometimes called the detected set of M. Okay, so that's sort of a precise description of what this set is in terms of this invariant. Okay, so maybe what's the idea of the proof? Well, this Dehn filling M of alpha is an L space if and only if, say, all essential intersections of HF hat of M with the line of slope alpha have the same sign. Okay, so for example, if I do manage to project one-to-one down to the circle, then it's pretty clear that all the intersections are going to have the same sign. And moreover, that if I wiggle the slope a little bit, that property is still going to be true. On the other hand, say that I'm not an L space, that I have maybe some essential intersection of L alpha with HF hat of M, maybe something that looks like this. Here's a puncture point, keeps me from moving. So here I have these two intersection points of opposite sign. Okay, and now here we come to the first application of freshman calculus. Right, the mean value theorem says that there has to be a tangent direction here which points along alpha. Okay, and that's how we see that this relationship between the L space filling slopes and this set of tangent vectors to HF hat of M. Okay. So, and maybe let's go back to the example of the trefoil. Okay, in practice, it's if you give me a picture of this HF hat of M, it's really easy to figure out what this set of filling slopes is. Maybe I had the invariant of the trefoil here. You might wonder, around the slopes to change. But if I just imagine that this thing is made out of rope, and I pull on it until it's tight, then what I'll get is a picture that looks like this. And actually, I can read off the set of tangent slopes from this very easily. Okay, they're everything in between minus infinity, which is this slope, and then I go all the way around till I get to this slope here. Have I drawn the wrong trefoil? I've drawn completely the wrong trefoil. Let's try to draw the right trefoil. Right, okay, so when I pull on this, I get a line like this. That's better. This here is basically the interval between minus infinity to 1. Okay. So maybe mention some corollaries of this theorem. So M is Floer simple. Then each of these curves HF hat of MS, well, I project one-to-one to the circle, so this is a simple closed curve. Okay. Well, that means that a simple closed curve is going to cut the cylinder into two regions. And so that actually means that this tau m of S bar is either 0 or 1 for every spin C structure. Right? Either I lie above the curve, and tau m is 1, I go down through it to get to minus infinity, or I lie below it, and tau m is 0. And then the last thing is that this set L of m is either a closed interval in the circle of slopes, or it's all of slopes of m minus a homological longitude. So let's call this option A and this option B. Okay, and I should mention that now these two properties were first, let's prove these first with Sarah. And then somehow, using other technology. But I think that this is the most beautiful proof of these facts, to think about these curves. All right, so now I think the thing that I really wanted to talk about here is what happens in option B. Sorry, in option A. Okay, so here the L space interval is, it's some closed interval. Okay, and I could ask, what are the endpoints of L of m? Okay, and so there's a very definite answer to that question. Again, this is a theorem that, well, I would say that I proved with Sarah, but really I should just say that Sarah proved. I suggested the statement, maybe. Let's state it this way. So but again, I think that this proof is, that I'll give is a beautiful proof. So let's say it this way. So in case B, where we have an interval of L space filling slopes, there's a set, let's call it script EC, inside of slopes on boundary M. You can think about this. This is the same as the projective space on the rationals, which sits inside of RP1, which is S1. Okay, that's completely determined by the Turayev torsion of M. Okay. And so the endpoints of L of M are consecutive points in C. So what does this set C look like? Well, here's the slopes. There's a special point on it, which is given by the homological longitude. And then this set C, well, it's sort of nowhere dense anywhere, except it has an accumulation point at the homological longitude. And what I'm saying is that the L space interval looks like something like this in that set. Have two consecutive endpoints. Points that are two consecutive points in this set that are the endpoints of the L space interval. Okay, so now in the remaining 8 minutes or so, I should tell you what the set C is and sort of why this might be true. So what's the idea of proof? I'll start to prove it, and then we'll get the set C coming out. Well, let's just say given my alpha in the interior of L of M, let's choose coordinates on H1 of M so that this line L alpha is just vertical. Okay. So now the projection along L alpha gives me a homeomorphism to S1. So if I just unroll the picture to the plane, what that means is that HF hat of MS is a graph. Let's say y is f of x, or some function f. Okay, so it looks like, it looks kind of like this. Here's a picture of what that graph might look like. And when I pull it tight, it kind of hangs on these corner points. Okay, and now the so this detected set of M is going to be the interval between the maximum value of f prime, the minimum value, and the maximum value of f prime. Right? Maximum, the largest and the smallest tangent slope. And I want to determine what those maximum and minimum slopes are. Okay, so now let's look at this graph. Okay, this graph hangs on the lattice points in this picture, right? We pulled the cord tight. And there are two things that can happen at any lattice point. Either it can sit on top of the lattice point, or it can sit underneath the lattice point. Okay, now, if it sits underneath the lattice point, okay, well, this curve, that means that the curve is concave down. Right, so by another application of freshman calculus, we know that f double prime of x is negative here. Derivative is decreasing. And similarly, if it sits if it sits under the lattice point, that means that f double prime of x is bigger than 0 here. So the places where I have the maximum slope, the minimum slope is going to look like this, and the place where I'm going to have the maximum slope has to look like this. Okay, and notice in both cases, what I'm really doing is I'm running in between a green and a yellow point, or a green and a red point. Okay, and so remember, these red points are the ones that lie under the curve. Okay, so this point here corresponds to a spin C structure with tau s bar equal to 0. And this green point here corresponds to a spin C structure with tau s bar equal to 1. So it lies over the curve. All right, so now we define this set, let's call it d tau bigger than 0. what is it? It's the set of all differences, let's say, S prime minus S, where, let's say, I of S prime equals I of S. Okay, so these are both relative spin C structures that live in the same, they live in the same picture for, live in the same absolute spin C structure, so in one of these pictures. And I have tau of S prime is 0. It's the curve, this is the red thing, it lies under the curve. Tau of S is 1, it lies above the curve. And in this picture here, we need to have the red thing above the green thing in absolute height. So let me just write that S prime is bigger than S. Okay, so if I look at this set here, so these points here are precisely going to give me these places where I get the maximum and minimum slopes. Okay, and then, so now I can say what this script EC is. So if J is the map from H1 of boundary M to H1 of M, then this set script EC was exactly J inverse of this set d tau bigger than 0 of N. Okay, so I suspect that I've used all the time, if not more. No, it says 4:59:44. So I think I will stop now. Excellent question. Right. So one thing that you could imagine you could do is you could count disks that go through the punctures and weight them with a U and ask yourself whether you actually got HF minus of M. And I think thanks to, well, I think that Jonathan knows that the answer to that question is no. In general, it's a little bit more subtle than that. But there are many cases in which you expect that it will be true. For example, I think that it's certainly true for all of these Floer simple manifolds that that's going to hold. But it's not going to hold in complete generality. Right. Currently, that set consists of the empty set. I mean, so I'll give you, right, so, another answer to your question, which maybe, which I learned from Robert and is, also a good answer, is say that I consider a manifold that's the connected sum of, my favorite manifold with torus boundary with some other, homology sphere, let's say, or rational homology sphere. And so, I didn't say this, but I should have. This invariant HF hat of M is, defined using CFD of M. Right? It's a way of packaging CFD of M. And in particular, what, if you think about this connected sum, you'll see that it can never see anything about HF minus of the thing that you summed in. All you're going to get is you're going to get one copy of, for each generator of HF hat of the thing you connected sum with, you're going to get a copy of your curve. Okay. Now, how, if you had a theory that encompassed HF minus, how would you resolve that in this picture? Well, the answer is that you have all of these parallel curves. They're probably going to come with a local system that carries some U's in it. So, and that's, so I think in some sense that's a place where a local system naturally should arise. But, there's not any theory to sort of make that work.